A simple building is shown here. A single room, and single-story reinforced cement concrete building. This is the typical skeleton of the reinforced concrete structure. The slab is supported by the beam. Beam is a structural member sufficiently long as compared to its lateral dimensions. Beam is supported on columns. The floor slab and roof slab will rest on the beam. So, the load from the slabs will be transferred to the beam. Before designing the beam, we need to know the forces for which it has to be designed.
Shear force and bending moment diagrams are powerful graphical methods that every mechanical and civil engineer should know how to use to analyze a beam under loading. In this video, I'll explain exactly how to master these diagrams, and we will see how they can be used to understand how a beam is loaded. Beams can be loaded in a number of ways, the most common being concentrated forces, distributed forces, and concentrated moments. Beams can also be supported in a number of different ways. They can have pin supports, roller supports, or be fully fixed, which each restrain the beam in different ways. Pin supports prevent vertical and horizontal displacements, but allow rotation. Roller supports prevent vertical displacements, but allow horizontal displacement and rotation. Fixed supports prevent all displacements and rotation. If a certain degree of freedom is restrained at a support, we will have a corresponding reaction force or reaction moment at that location. For example, rotations are permitted for a pin support, so there is no reaction moment, but displacements in the vertical and horizontal directions are prevented, so we will have horizontal and vertical reaction forces. So how do you determine the shear forces and bending moments within a beam? There are three main steps we need to follow. First, we draw a free body diagram of the beam. This shows all of the applied and reaction loads acting on the beam. The next step is to calculate the magnitude of the reaction forces and reaction moments at all of the beam supports. We do this using the concept of equilibrium. To maintain equilibrium, all of the forces in the vertical and horizontal directions should cancel each other out. Similarly, all of the moments acting at every point along the beam should cancel each other out. This gives us a set of simple equations we can solve to calculate the reaction forces and moments. If we can calculate all of the reaction loads using the three equilibrium equations, the beam is said to be statically determinate. For some beam configurations, like this one shown here, we won't be able to calculate all of the reaction loads because we have too many unknowns and not enough equilibrium equations. In this case, the beam is said to be statically indeterminate. This beam has 4 reaction forces, but we only have 3 equilibrium equations. To solve this beam, we would need to use slightly more complicated methods and consider boundary conditions. In this video, I will only cover statically determinate cases, where we can use the equilibrium equations to calculate all of the reaction loads. Once we have calculated all of the reaction loads, the third and final step is to figure out the internal shear forces and bending moments at every location along the beam. Let's take a look at an example of a beam with pinned and roller supports, loaded by 2 concentrated forces. First, we draw the free body diagram. We can then use the equilibrium equations to determine the unknown reaction forces at point A and point B. We will start from the left-hand side of the beam. Let's draw the free body diagram for a location immediately to the right of the 12 kilonewton reaction force. To maintain equilibrium, the shear force must be equal to the reaction force. We can draw this on our shear force diagram. The shear force will be constant until we reach the next applied force. The bending moment must be equal to the 12 kilonewton reaction force multiplied by the distance x to the reaction force. This gives us the equation for a straight line, which we can draw on our bending moment diagram. We then repeat the process by moving the location of our cut further to the right. This time we place the cut immediately after the 15 kilonewton force, and we draw the free body diagram again to determine the shear force and the bending moment. We repeat this process until we have covered the full length of the beam. We end up with the complete shear force and bending moment diagrams for the beam.